Continuing with our discussion on device service routine, before we take a look at, in fact, an integrated look at the evolution of I/O, we will start today's coverage with the one that is still pending, that is the DMA, or direct memory access. We had earlier seen what sort of program segment or software is needed for the, in fact, it is only a small segment, 2 lines or 3 lines, whatever we saw, for programmed I/O and then on interrupt service, right. Now, DMA, let us take a look at it. Now, we know that in the case of DMA, the processor is not involved, correct, and it is in fact cut off from the system. So, the device will directly access the memory. Now, in the case of input, the device will access and then it will be putting the data in the memory. In the case of output device, from memory it will be, the data will be routed out to the towards the device. So, the I/O interface or the controller that takes care of the device interface will in that particular one be essentially a direct memory access controller, or just DMA controller. Okay. So, we had seen that since the processor is not involved, and that is in the case of programmed I/O, processor is very much involved. In the case of interrupt, processor is asked to be involved, and in the case of DMA, processor will be informed, okay, a very fast device is coming, there is going to be a very fast data transfer. So, you just cannot handle, so keep away, this is the kind of a thing, right. So, the device when it is ready will inform the CPU, fine, will inform the CPU obviously over the bus lines, So, we will just take a restricted view of some of the signal lines. Okay. So, I will keep switching between this and that. So, there is going to be some request, it is very much like interrupt. Okay. Now, in the case of interrupt, when the device is ready, the device interrupts the CPU and then the CPU is involved. Now, in the case of the DMA, the CPU will similarly be interrupted, though it is not called interrupt. Okay. It will just say, okay, keep off, in other words, hold off from the entire scene, right. This is one name for the DMA request. It is nothing but hold is nothing but a DMA request signal. Okay. DMA request signal, in some places they call it just hold. So, the device which is ready, right, that is the, in fact, as I said, that this one will be a DMA controller, the I/O interface. So, this will generate when this particular device is ready, okay, and the CPU will have to relinquish the bus, and then that is CPU may be doing something. So, it has to be allowed to be completed up to some point, and then the response from there will come. In other words, this may be called a DMA acknowledgement. Okay. DMA acknowledgement, let us say. In some they would say hold acknowledge. If you use hold as the input, then this may be called hold acknowledge. Okay. Just same, 2 different names for the same thing. So, a request goes to the CPU and the CPU responds. It is similar to what we had in interrupt, is it not? In the case of interrupt request went to the CPU, and then the CPU sent an interrupt acknowledge, agreed, except that this is fast, and so in subsequent one, that this one is not going to be involved, that is CPU is not going to be involved. That is the difference between these two. Of course, there are other minor differences. All right. Now, the hold is another input to the CPU which comes over the bus, and the hold acknowledge is another output from the CPU which goes over the bus, and it must go to this. Now, like we had seen in the case of interrupt, here also there can be more than one device requesting, possible, but generally it may not be. Why? Because what we are talking about is very specialized situations when you have very high speed device and so on. Okay, it is possible that there may not be as many. Okay. So, one has to also bear in mind there can be more than one DMA device, that possibility is very much there. There can be more than one DMA device, all right, fine, good. Now, if this is the situation, what is the kind of programming that is involved in this, that is the device service routine. After all, the CPU is not involved in the service at all, am I right? The CPU is cut off from the bus. So, it is the DMA controller which takes over the role of CPU and masters and sits at the master of the bus and then regulates, agreed. So, before the CPU can relinquish, if at all, something must be sent to the DMA controller, agreed. Something must be sent to the DMA controller before the CPU relinquishes the bus, because once the whole input goes and then CPU relinquishes the bus, there is nothing that CPU can do. So, you can see that this particular device service routine will be subsequently run by the DMA controller, not by the processor, because processor is out of the picture. But then the CPU as the general master of the bus must have indicated to the DMA controller earlier, okay, you can expect possibly 1 kilobytes of data or 10 kilobytes of data or whatever, and then when that comes, store it starting from say location 1000 or 10,000 or whatever it is, some address. Okay. So, this we have seen. So, essentially this particular device service routine is mostly during the configuration phase, is it not? We have always talked about two phases during I/O. One is configuration phase and the other is actual data transfer phase, agreed. So, during configuration these two things must be done, that is we had already mentioned this earlier. What is that? First, how many bytes to transfer, okay, assuming it is only bytes, how many bytes to transfer. In other words, what is the block size, okay, the same thing as saying what is the size of the block of data, right, block size, what else, and then where exactly it is to be stored from, where to store, that is in the memory, or where to read from the memory. I always say store mainly because I always have input device in mind, right. On the other hand, if you are thinking of an output device, obviously where to read from, correct. Again memory is involved. So, storing in the memory, we are talking about reading from the memory and outputting to the device, that is in the case of the output device, good. Now, where to store, in other words we can also say what exactly is the starting address of this particular block, right, starting address in the memory, start address in the memory, from where this block must start, okay, that's from where the first where the first byte is to be stored. So, sometimes you may say start address or the first byte and then the extent, right, extent, there is a block size, how far it will extend, okay. So, these things must be stored in the DMA controller, and that will be done by the CPU during configuration phase. Now, we always said what I/O consists of configuration phase and data transfer. Now, since CPU is not involved in the data transfer, CPU's job is over with the configuration phase, because that is all the CPU is involved in. So, these two things, what is it like, let us say for instance, as part of the configuration, okay, the software segment would be say something like we will follow what is the format we followed earlier, move destination comma source, right, that is the format. So, we will say move what, the where to the DMA controller it must go, right. So, move to the DMA controller, and where should it actually go? I will just say, for instance, I am assuming a command register is there in the DMA, okay. A command register is there, and specifically within the command register I may have to move to the part which is going to store the block size, okay. So, move to this command register, well, whatever is the size of the block, assuming that okay, we have to really bother about the syntax of that. So, I will just say number 1000, which means 1000 bytes, okay. This is a syntax I am just following arbitrarily. Move number 1000 to block. Basically, this would tell the DMA controller that up to 1000 bytes can be transferred, and the other part what? Start address. So, move what? Start address, okay. Move the start address, well, whatever that address is, move the start address to the same command register, but to which part? The part which will hold the address, okay. So, essentially you can see that the CPU is writing something into the command register, is it not? When you write something into the command register, you are actually CPU is actually issuing a command and defining certain parameters, what it should do, right. Fine. As far as the CPU is concerned, essentially these are the two instructions basically in preparing for DMA transfer, that is all, over, fine. Then rest of it DMA controller must do. So, in the case of the DMA, a study of the DMA controller is more important, what it does. For instance, now we know that like in any other interface chip, this controller will have a command register, status register, and so on and so forth, and then there may be other things. For instance, you may be having in fact we have commercially available DMA controller chip which can take care of 4 devices at a time. Generally those things will be called channels, that is on over 4 channels, okay. We talk about a 4 channel DMA controller. That means basically it means over I have just shown one device here, instead there will be 4, right. And then when any of these 4 devices puts up a request, rather it is not just the device request, it will be like this. What are we talking about? We are talking about a block, okay. So, now for 4 devices connected over 4 channels, there must be 4 sets of command registers, okay. Some of them may be common, but then certainly block size, starting address, they will all be different, no. So, there must be 4 sets, and then possibly there will be 4 blocks. For instance, the device may store what is it, I said 1000 here, no. Let us say 1000 means basically the DMA controller will be having possibly a buffer size of 1000, in which case while actual transfer takes place with the memory, okay, this is cut off. The DMA controller will be involved in with the memory here, right, is it not? So, in the actual DMA transfer, from the buffer it will go to the memory if in the case of input device. But on the other hand, if the device is very fast, then there will not be any problem, okay. This itself will keep collecting the data and then passing on to the memory. So, anyway, so these are all some variations. Then when you have 4 channels, then what is it? We have come across this situation earlier, no. Let us say if there are 4 devices interrupting, then we talk about priority. The same issue comes here too. You have to look into the priority among the 4 channels. Normally this will be built in, okay. Normally this will be built in, saying channel 1 is a higher priority than channel 2, which is a higher priority channel 3, and so on and so forth. But then one can change the priority also. We have talked about earlier in the case of interrupt, right? That is called software definable priority, right? Good. So, these are all certain additional things. Now, getting back to the program that is needed. So, the DMA controller is set up by the CPU with the issue of these bits of information, and that is part of the whole show. Afterwards, when the device is ready, the DMA controller will indicate to the CPU it is ready. Then the CPU at a convenient time, I had mentioned earlier what is a convenient time. At a convenient time, it will stop processing, and then it will generate the acknowledge. On seeing the acknowledgement, okay, the device will start doing the data transfer between the device and the memory. That is why it is also called direct memory access. Directly the memory is accessed, or the DMA, right. Good. This is as far as the data transfer is concerned. Now, in the data transfer, this is the one which is going to do, and this will be very fast. As I said earlier, it will be something like a machine gun. That's at such a fast rate it will go. That's one clock, 2 clocks may be enough. Whereas here one may have to introduce the CPU, the processor may have to execute a few instructions. Okay, after a few instructions, it may have to check this and so on and so forth. Say maybe the status, maybe the device is ready, etc. Okay, all those things. Whether maybe during transfer any error has been committed and so on. There is no room for such things here. Okay, in case of error, that's all. The whole block is going to be erroneous. So forget about it. Good. So all those things will not be done. They place the address, send the data. Place the next address, send the data. That's all. It will go on. So starting from some address, this address plus 1, then plus 1, plus 1, plus 1. Okay, it will go so fast. That's why it is used for very fast devices. Now, fast in the sense which the CPU cannot otherwise have handled, right. So that's why now you can see that the DMA controller, or this what you may call in general as the IO interface, that takes the role of a processor, right, because there is no master. The CPU is not minding the bus, it is not mastering the bus. So CPU is not minding the data transfer. So this is, now this in fact is a very good point now to start talking about the next thing, that is the IO evolution. As I said, this is the nice point in time to trace the evolution of IO. Now, let us get back to our original diagram. So, you have the CPU as the master of the bus, then you have the memory, the IO. So, we had taken a look in our first part of these lectures about the processor, and in the second part on the memory, and then the interaction of memory and the processor. And now in the ongoing third part, we just looked at the essential or basic 3 modes of data transfer, that is which involves the IO. And we noted that it is programmed IO, interrupt driven, and then the DMA. Now, progressively you can see the CPU was involved in programmed IO. The CPU was involved even in checking whether the device was ready in programmed IO. In the case of interrupt driven, CPU was involved, but then only when the device indicates that it is ready. And then in the third one, the CPU was involved only to the extent of shutting itself off. That is, when the device says it is ready, the CPU goes off the bus, and then the IO controller, specifically the DMA controller itself, takes over. Okay. Now, you can see that the sophistication of IO has been increasing, right. Earlier it was enough for, in the programmed IO it was enough if the CPU just checks that, and then this is a passive one, right. It will only respond to the processor. Then in the interrupt case, it became active, in the sense when the device says it is ready, it will actively inform the CPU that it is ready. And then in the third case, we saw that it became really more active. How? Not only it informs, but it also not only it informs the CPU, it also takes over the function of CPU. So, this in fact, that is why I said the evaluation of I/O is a nice thing we can talk about at this point in time, mainly because we might say that the various stages in the evolution of I/O have contributed over years, over decades in fact, to the present state of art of computing. Now, let us take a look at it. How is it? Something like about 8 or 9 stages of evolution I will trace, part of it whatever we have talked about. First thing, okay, the first stage, that is the if you want call it as pre-computer historic age or just dawn of computer age or whatever, right? It was like this. See, right from those days, it is always processor, that is the CPU, the memory and the I/O. Essentially, what is I/O? I/O consists of a few terminals, or in process control application, it will consist of a few transducers which change transduces some of the analog signal into digital and then communicate. Okay, either way, we can call this as T for transducer or terminal or whatever. So, you can see that essentially P, M and T, these are the 3 main elements of any computing system, right. Now, let us just see. In the earlier days, okay, the processor was directly involved with the T. How? Somewhat like this. That is, the processor was not only interacting with the memory, but the processor was also involved with the I/O. For instance, in programmed I/O, that is what we are seeing, is it not? So, in the first stage, processor, you may say processor directly controls, okay, directly controls T. That is, well, this cannot be avoided, processor interacting with memory anyway. Why should we avoid? Both of them are anyway taking working at electronic speeds, there is no problem. But generally the problem is here, because processor works at electronic speed and mostly this will be at lesser speeds mostly. Now, so the first stage in which the processor directly controls T, or even in the case of programmed I/O, that is what it is. Programmer, sorry, not programmer, processor, P for processor. Processor checks whether the terminal is ready or device is ready and then affects the data transfer. So, directly it controls that T. Now, in the second one, okay, a simple controller, we may say, gets introduced. A simple controller in the sense the processor is not directly involved with T, but in somewhat. So, we can say a simple controller is introduced. Okay, we will just call it as K. The sense we have the memory, of course, that cannot be done away with, and we have the processor, and between the processor and the terminal or the transducer, we have a simple controller, right. Now, this processor is a very general purpose processor. This specifically as far as the I/O part is concerned, okay, but it will be a very simple one. Now, we can say this way, this I/O interface can be considered as that K, okay. That is, in other words, originally this I/O interface possibly was part of the processor itself, with some extra circuitry. Now, you are slowly separating that. Okay, this you can consider as the K. So, now you can see that the idiosyncrasies of these devices can be hidden here, and at this end only some standard protocols can be established. Okay. So, like that a simple controller K is introduced. Okay. Now, the third stage of evolution, we can talk about the simple controller, okay, which becomes a little more sophisticated. So, you would say the controller K with interrupt feature. Okay. Now, you must be able to see. That is, earlier the processor was checking with the controller and seeing whether the controller says that the device is ready. That is how it was doing. Now, the controller becomes a little more sophisticated in that when the device is ready, when T is ready, when terminal is ready, okay, the controller informs the processor through the interrupt. So, this is the third stage of development. Okay. Then the fourth, you may be able to guess yourself what is that. The controller K with the next one, what is it? A simple controller, programmed I/O, now interrupt. So, the third is DMA. Okay. K with DMA feature, that is the controller not only informs the processor when it is ready, but then the controller can also access. Now, how is it possible? Can access what? Can access the memory. Okay, when this one. So, we have to slightly modify this, that is, we have the memory M and the processor deals with it. Now, we have the controller K, okay, which helps T access the memory if necessary directly. Agreed? So, instead of this arrangement, because earlier in the case of interrupt also, when the device is ready, the controller will inform the processor, then the processor executes the interrupt service routine and moves the data from, say, if it is input device, from the device to the memory. So, the processor was involved even in this case. Now, whereas in this case the processor can be removed, the controller can directly access the memory. So, that between device and memory the data transfer can take place depending on input or output, the direction will change. Okay. What is the next one? Next one would be this K controller becoming little more sophisticated or complicated, some more complex feature, right. First it was processor, then with the introduction of the controller we keep seeing that more and more feature gets added. So, obviously, the next one will be what? We can say that the controller has come with not only direct memory accessing capability, because just a few minutes back we were looking at, no, in the case of DMA the processor will inform the controller what is the size of data and where to store. Now, just as per that the access will be taking place and the data transfer will be taking place. Suppose if the controller has a few more instructions, I mean can execute a few more instructions, then slowly it can take the role of the processor itself, no. So, now we can say controller K with some kind of an instruction buffer. In fact, that instruction can as well be issued by the processor prior to the access. Now, what is it? During DMA, okay, a simple data transfer takes place. And for before the DMA takes place, the processor issues some commands, rather we can say issues some instructions. Now, in this particular case, the processor issues quite a few more instructions, and the controller has the instruction buffer, okay, and during that particular access it will execute those things. Okay, just a little more complex situation. All right. Then the next stage, what would you expect? This particular controller becoming almost like this processor, because we earlier was doing DMA, then we set some more instructions. We didn't in fact elaborate what instructions, some more instructions will be capable of. Now, let us say it is really executing some instructions of its own, that is the processor need not tell what to do. Of its own it may have its own, that is inbuilt instruction. So, we can say, we can call this particular thing as the controller becoming an IO processor. Okay. So, we can say an IO processor, okay, with what? Special instruction set, that is its own instruction it has. Okay. In fact, chronologically speaking, this has happened. For instance, in the case of Intel, 8089 is a processor, IO processor. This is a classic example. Intel 8086, when 8086 came as the main processor, okay, this one K becoming an IO processor, that is K becoming more complicated and thus becoming an IO processor has happened. Intel 8089 is a classic example of that. So, now what is it? This gets changed somewhat like this, a little what? Memory, then you have the processor, that is a general purpose processor, let us say 8086 if it were Intel, then this becomes an IO processor. Okay, that is a controller becoming an IO processor involving in data transfer. So, now this is a general purpose processor, this is an IO processor. We can call this also as channel processor, right. In the case of mainframe, these channel processors were very much in use, and these things were realized in the case of microprocessor also. That is how it came, right. So, its one processor, that is the processor is essentially concerned only with the main processing, and as far as IO is concerned, it will just churn out some data and hand over saying what to do, and then the IO processor will take care of the rest. The situation is not very much different from here, except that here the processor continues to remain the master of the bus, whereas here it is something like the processing IO processing function has been delegated to this, and that takes care of. Okay. Now, in the seventh stage, what do you expect? The controller was becoming more and more complicated. Then finally, controller became the IO processor, and in fact, it is very much sitting like as a challenge to the main processor itself, though its function is restricted to IO. So, the next one would be what? When you look at it, these developments, what comes to your mind? Some more resource for this processor if provided, that is what happened. That is, the IO processor, okay, or IOP comes with its own local memory, okay, with its own local memory in the sense like this. The main memory is there, then you have the main processor, Now you have, earlier you had the I/O processor, which was essentially dealing with the terminals or whatever. Now we have a local memory. That is, I/O processor has its own memory. Now, if you just look at this part, the bottom part, does it remind you of something? What is this? Same thing. So, it is very much like the natural biological cell growth, some cell dividing and then growing by itself. No, the same way here also it has come. In fact, this whole thing, now you can call it as I/O. For instance, the bus may be called an I/O bus, right? So, you have now the main processor, main memory, I/O processor, and I/O or local memory, local to that, and then this. Now, what happens? This memory and this memory is not going to be very much different, in the sense the processor can churn out a block of data, right, can carry out some processing and transfer to this memory and then say what is to be done with, and then the processor deals with this and goes on. So, this acts very much like a buffer now, and whenever this one has done and this say memory is empty or whatever was there has been already input or outputted, then the processor will start filling in, right. So, the I/O processor with local memory. Now, when we talk about local memory, as I said, this whole thing can be considered as sitting on I/O bus and this as the main bus. So, that's how even buses have grown. So, you will have some bus for very fast thing and then some low speed bus for I/O. Okay. So, bus evolution also is very much involved with these. Now, the 8th step, what do you expect? The I/O processor is becoming very powerful. Okay. So, actually that is what it is. The IOP or the I/O processor, now we may say with I hope I can say same or at least similar, same or similar instruction set as the main processor. Okay, set as the main processor. Is it just an imagination or did it really happen? It had happened. In fact, in the case of Intel 8089, it had happened. In the case of Intel family, not 89. First 8089 came, and this particular one is nothing but Intel 80186. That particular processor, though developed as a general purpose processor, really became quite useful because of certain functionalities as an I/O processor. So, even to this day you will find 80186 based device controller boards, okay, which will take care of multiple devices and so on. So, that is what it is. So, now there is no difference between this and this. For instance, you can have an 80286 or a 386 or a 486 memory, and then here 80186 will be sitting. May not be very powerful, certainly it is powerful from I/O point of view, that is what it is. Good. Now, 8 stages had been traced. Now, what do you think is possibly the next one, which we may put it as the ongoing or current development, the 9th stage? Like the main processor was giving birth to a specialized I/O processor, now we can have one processor which can handle one type of data. Graphics, a graphics processor, okay, for handling graphics you have a special processor, Okay. Similarly, if you have audio data, well, have another processor. If you have video data, have another processor. Okay. If you want one type of graphics, you have one processor. You have another type of graphics, have another processor, and so on and so forth. So, what has happened is, in other words, we can talk about the ongoing thing, or what is still evolving, as something like distributed I/O. In the sense, there is, you are not having one I/O processor, but you are having multiple I/O processors. Multiple I/O processors. When I say multiple I/O processor, it is not just n types of same processor. It will be, each one can be different one. So, that is what we are having even now. For instance, we call them as accelerators. We talk about graphics accelerator, we talk about video accelerator, is it not? So, what are they? So, we talk about graphics accelerator, we talk about video accelerator, which means these accelerator boards are essentially going to have a special type of processor. For instance, yes, in the case of DSP, handling digital signal processing, you have special DSP processors. So, for handling special signals, you have special processors. That is what we are talking about, right? So, multiple I/O processors, and for different types, meaning what I mean is for different types of data. Okay. Let us put it in very general way, different types of data or different types of processing. Okay. You have different processors, each with its own capability and capacity, right? That is what it is. Now, trace back, we started with this, and we said at block diagram level we can talk about 3 items in general. Right at the beginning itself, we knew that we had to deal with different types of devices. Okay? And then while discussing memory, we had also come across different types of memory. And now what are we talking about? We are talking about different types of processors, right? Different types of processors. So, now what is the next step? I mean, it is, in fact, that is also ongoing. We started with one memory, one processor, one memory, many devices, and then many memories, and now many processors. In other words, the situation is multiple processor in general, and then when you distribute the function of this processing, okay, with reference to the specific processing need, like text processing, graphics processing, audio processing, or the type of data like video data or audio data, okay. Then if you have special types of processors, or for that matter directly handle the signal, in which case we talk about digital signal processors, DSPs. What are DSPs? DSPs are also processors, they have that same capability, right. So, now slowly from one of each we have gone into n of each, in other words multiples, right. Now, when things have evolved like this here, in fact, we have traced specifically with reference to I/O, but earlier we have also talked about different types of memory. We are not talking about the evolution and all in general. Now, if one of each has gone as n of each, that is multiples, now what about this bus? Bus also can, right. So, similarly we have in fact we have seen it already here. What is it? Here in this particular one we are talking about a general high speed bus and a special low speed I/O bus, is it not? So, one bus here and another bus here. Now, in the case of DSPs, I was talking about digital signal processors, right? You would note that there will be a special instruction bus and there will be a special data bus. Why? Because instruction and data both go from the memory, and once when a data is being processed, it is possible to fetch the next instruction and keep it ready, which generally we refer to as pipelining. Keep it ready in anticipation that is the next instruction that will be used. It may or may not be used. So, you parallelize the activity, right? You parallelize the activity. Now, to support this multiple buses, sometimes even this will be split into, for instance, instruction memory and data memory. I think I had indicated that earlier. And then I also said, when you have that what is known as Harvard architecture comes, that is the one which has instruction bus and data bus separately, and the memory connected to that will appropriately be instruction memory and data memory. So, now you can see that slowly things are growing more and more complicated at each subsystem level, and hence it is becoming very complicated at the system level too. In fact, we have not gone into the details of instruction fetching, right? We just said instruction is fetched, but actually when an instruction is fetched and then when it is being processed, it is possible to fetch the next instruction, right? And if execution of one set of data takes some time, it is possible to break down those things and then carry out a lot of parallel activities, some of which maybe we will see in the later lectures. Now, for now you can just see how really this evolution has really taken place, and in fact, we have historically two instances, as I was mentioning in the case of I/O, and then you should also be able to really understand how a single thing has become multiple things, and all just because of semiconductor technology evolution, right? Essentially, it is that particular one which has been, because today if 1 meg is available and next year if 4 meg is available, and accordingly the applications also make these demands. And then what was possibly say a restriction in the size of say the program breaks down because more memory is available. When more memory is available, then there is more demand, and then the processing need also goes up. Like this it keeps on going. Fine. Now, all these for what purpose? The purpose is, when you have different types of processors for different types of data or signal, does it not remind you of something? The tendency is to become natural. For instance, if you say that man is a natural, is part of nature. Now, all the natural processing capability which he has, for instance, he has eyes specifically for seeing, he has ears specifically for audition, and then of course mouth and other related system for producing the speech, and so on. In other words, different senses. For different senses, we have different transducers. So, similarly, here, who knows, we may have tomorrow a general purpose processor, a speech processor, maybe who knows, for feeling something, for smelling there may be a processor, and so on and so forth. So, the tendency is really for the computing system to go as close as possible to natural processing system, that is human level. So, that is how the trend is. Good. So, in the next lectures we will take a look at some of these I/O devices, because we have to complete that part, and then come back to this overall situation.